Nobody told you this when you were a kid looking up at the stars. They gave you the basic version. Big, they said. Old, lots of stars, far away. And you nodded and said, yeah, okay, lots of stars, and moved on, because the basic version doesn't do anything to you. It doesn't get under your skin. It doesn't follow you home and sit in the corner of your mind for 3 days while you're trying to fall asleep. But the real version does. So here's the real version. The Milky Way is not just big. It is so incomprehensibly, almost offensively vast that every metaphor humans have ever tried to build for it immediately collapses. It is not the size of a city. It is not the size of a continent or a planet or a solar system. It is 100,000 light-years across, and if you tried to drive across it at highway speed, it would take roughly 1 billion years. Not metaphorically, calculably. 1 billion years of driving. And that's just the width. That doesn't account for the halo, the dark matter envelope that extends the effective gravitational reach of the galaxy to something closer to 300,000 light-years. The part you can see, those hundreds of billions of stars smeared across the night sky in a pale arc from one horizon to the other, is just the lit-up portion, the detectable minority. And here's the part nobody says out loud, because it sounds too strange. You live inside it. Not near it. Not below it. Inside it. Right now, the galaxy isn't something out there. You are inside the Milky Way the same way a speck of dust is inside a building, except the building has 200 billion rooms. And each room is a star, and most of them probably have planets, and nobody has ever done a complete tour. That's where this starts. The word galaxy comes from the Greek word for milk, gaela, milk. The ancient Greeks looked up at that pale smear of light and called it the Milky Circle, Galaxias Kyklos, and then the Romans translated it to Via Lactea, the Milky Road, and it's been some version of that ever since. Milk, because that's what it looked like. Not like fire, not like electricity, not like anything sharp or blazing. Soft, diffuse, like light spread too thin, like the afterglow of something that couldn't quite hold itself together into a single point. Every culture that has ever existed under a dark sky has named it and built stories around it. The Maori of New Zealand called it Te Ika a Maui, the fish of Maui, the demigod who pulled New Zealand up from the ocean floor with a magical fishhook, according to their tradition. The Milky Way was the cosmic form of that same act of creation, stretched across the sky. The Aboriginal Australians of the Kamilaroi people read the dark patches between the stars, not the stars themselves. The dark lane of interstellar dust that runs through the center of the Milky Way's visible band, those dark gaps were to them the shapes of animals. An emu, a goanna, the dark constellation that you can only see if you understand the sky well enough to read the negative space. The Maya built their cities in alignment with the Milky Way's arc. Their sacred saber tree, the world tree connecting the underworld to the sky, was mapped directly onto the structure of the galactic band. The densest, brightest region of the Milky Way, the one that points toward the galactic center in Sagittarius, was the root. The tree grew upward from there into the dome of the sky. When they looked up, they were looking at cosmology made literal, architecture in response to it. The ancient Egyptians placed it above the Nile Delta during the flooding season and called it the Celestial Nile. 2 rivers running parallel, one giving life to crops, one giving structure to the night. All of this, for most of human history, was just there. Every clear night. Just there. The idea that you might live somewhere with enough electric light to make it invisible would have been incomprehensible to any of these people. The Milky Way was the sky. You couldn't separate them. You looked up and there it was, always, from infancy to death, every cloudless night of your life. Background and foreground at once. For most people alive today in cities, it has vanished. Light pollution has quietly erased one of the longest-running features of human experience. The fact that you have to drive to the middle of nowhere to see something your ancestors saw every single night of their lives, that's worth sitting with. Let me tell you about the structure, because the structure is where things get genuinely unsettling in the best possible way. The Milky Way is what astronomers call a barred spiral galaxy, which means it has a flat disk shape with two dominant spiral arms curving out from the center, and at the very center, instead of a simple round hub, it has a bar. A long, dense, elongated region of stars that runs through the core like an axle, maybe 27,000 light-years long end to end. The arms attach to the ends of this bar and sweep outward in the shape that appears in all those artist renderings, that elegant pinwheel, those curving lanes of stars and gas and dust. We know this about our own galaxy only because of a combination of radio astronomy, infrared imaging, and a lot of careful inference, because we are inside the structure trying to map it from within. Every other barred spiral we've ever studied, we've had the luxury of viewing from the outside. The Andromeda Galaxy, M81, NGC 1300, all those beautiful Hubble images. We get to see the whole thing laid out like a photograph. The Milky Way, we are inside. Mapping it is like trying to sketch the blueprints of a building while standing in one room of it, in the dark, with only a flashlight. What we've worked out, painstakingly, over decades, using the radio emissions of hydrogen gas and the motion of stars mapped by the Gaia satellite, is that the Milky Way is not a simple two-armed spiral. It has two major arms, the Perseus arm and the Scutum Centaurus arm, and several minor arms or spurs, including the one we live in. The Orion arm, sometimes called the Orion spur. We live in a secondary arm, not one of the two main spirals. We're in an offshoot, a spur. We are in the galactic equivalent of a side street, not a boulevard, and our position within that spur matters enormously. We're roughly 26 to 27,000 light-years from the galactic center, which puts us about halfway out from the core to the edge of the disk, not in the dense, dangerous, radiation-soaked inner regions, not in the sparse, cold, metal-poor outer reaches, right in the middle distance. The galactic suburbs, as astronomers sometimes call it, usually with some combination of humor and genuine astonishment at how specifically positioned we are for the conditions that led to our existence. If we were closer to the center, the density of nearby stars would be higher, more supernovae in our neighborhood, more hard radiation. The electromagnetic environment would be hostile enough that complex chemistry, the kind that produces life, might not get enough time to do its work before getting disrupted. If we were in the outer regions, the heavy elements wouldn't be there yet. The outer disk is metal-poor, meaning it hasn't had as many generations of stellar evolution building up the carbon, oxygen, iron, calcium, silicon that complex life and rocky planets require. We would be trying to build chemistry with an incomplete set of ingredients. This position, 26,000 light-years out, on a minor arm, in a relatively quiet patch of the galaxy, is not a coincidence. It's not design either, not in the intentional sense. It's selection. We couldn't have formed anywhere that didn't have these conditions, so here we are. The center of the Milky Way is in the direction of the constellation Sagittarius. On a dark, clear night in the southern hemisphere in summer, or the northern hemisphere in late summer, that part of the sky is the thickest, the most complex, the most layered region of the Milky Way's visible band. You can see the glow of it even without knowing what you're looking at. The sky is just denser, there. More texture, more depth, but you cannot see the actual center with your eyes, or with any optical telescope, regardless of how powerful. The galactic center is hidden behind clouds of interstellar dust, so thick that visible light cannot pass through them. If you want to look at the galactic center directly, you have to switch to infrared wavelengths, or radio waves, or X-rays, anything that can penetrate the dust. And when you do switch wavelengths, when you point an infrared or radio telescope at the galactic center, what you find there has changed astronomy permanently. There is a supermassive black hole at the center of the Milky Way. It's called Sagittarius A star, SGR-AA Zektite. The asterisk in astronomical naming convention is pronounced star, so it's Sagittarius A star, and it has a mass of approximately 4 million solar masses, 4 million times the mass of our Sun compressed into a region smaller than the orbit of Mercury around the Sun. The boundary of its event horizon, the point of no return, the surface beyond which light cannot escape, is roughly 12 million kilometers across. In space terms, that's tiny. The Sun is 1.4 million kilometers in diameter. The event horizon of SGR is about 8.5 Sun diameters across, 4 million solar masses in 8.5 Sun diameters. In 2022, the Event Horizon Telescope collaboration released the first photograph of it. A global network of radio telescopes working in concert, effectively turning the entire planet into a single enormous dish, captured an image of a glowing orange ring surrounding a dark center. The ring is not the black hole. Nothing glows inside the event horizon. The ring is material, superheated gas, swirling around the outside of the event horizon, heated to millions of degrees by the compression and friction of infalling matter, emitting radiation at the point just before crossing the threshold. The dark spot in the middle is the shadow, the visual signature of the absence, the silhouette of a place where even light has been claimed. Looking at that photograph, knowing what you're actually looking at, is a specific kind of experience. That dark spot in the center of a glowing ring is the most extreme object in our galaxy. It has been there for most of the galaxy's life, growing slowly as gas and stars fall into it, shaping the gravitational environment of the inner Milky Way. It is the anchor around which everything else orbits. Right now, every star in the Milky Way is orbiting it, including ours. The numbers around that orbit are worth letting settle. Our Sun takes approximately 225 to 250 million years to complete one full orbit around the galactic center. One full lap. This unit of time has an actual name in astronomy, a galactic year, sometimes called a cosmic year. The Earth is roughly 4.5 billion years old. That means our planet has been around for approximately 18 to 20 galactic years. In galactic years, Earth is barely old enough to have finished high school. The last time the solar system was in the position it occupies tonight, relative to the galaxy, was approximately 250 million years ago. That was the end of the Permian period, the worst mass extinction event in Earth's history. 96% of all marine species wiped out. 70% of all land vertebrate species gone. The Great Dying, some paleontologists call it. The continents were still fused together into Pangaea. Dinosaurs hadn't appeared yet. Mammals hadn't appeared yet. The organisms most people could identify from a biology textbook didn't exist. And since then, the solar system has made exactly one loop around the galaxy. In that one loop, everything ended, and everything began. The Permian extinction ended. The oceans restocked themselves over millions of years. The Triassic began. The first dinosaurs walked. Pangaea broke apart. The dinosaurs dominated for 150 million years. The asteroid hit 66 million years ago. Mammals diversified into the available ecological space. Primates appeared. Great apes. Hominids descended from trees. Homo sapiens emerged somewhere in Africa, maybe 300,000 years ago. Left Africa. Spread across the world. Developed language, art, agriculture, cities, writing, mathematics. Built the pyramids. Wrote the Odyssey. Discovered heliocentrism. Mapped the genome. Walked on the moon. All of that happened in one galactic year. one orbit. The spiral arms of the Milky Way are one of the most commonly misunderstood things in astronomy. People assume the arms are fixed structures, that stars in the arms stay in the arms, rotating together like spokes on a wheel. That's not what's happening. The arms are more like traffic jams. Imagine a highway with 3 lanes and one very slow truck in the rightmost lane. Cars pile up behind it. The density of vehicles in that region of the highway is temporarily higher than the surrounding road. As cars pass the truck and speed back up, the cluster of vehicles doesn't move with any individual car. The traffic jam has its own velocity, its own behavior, separate from the vehicles that compose it at any given moment. Individual cars enter it, slow down, move through, speed up again on the other side. The jam persists as a pattern even as its membership changes constantly. Spiral arms work like that. They're density waves, patterns of slightly compressed gas and dust and stars that propagate through the galactic disk at a different speed than the individual stars are orbiting. Stars enter an arm, pass through it over millions of years, and emerge on the other side, continuing their orbit. The arm pattern persists because gravity keeps organizing the density into that configuration, reinforced by the self-gravity of the compressed material, reinforced by the bar at the center, driving the wave. What makes the arms important is what happens when gas clouds enter them. The compression of the density wave is enough to trigger star formation. The arm is where the gravitational squeeze tips molecular clouds over the threshold, and they collapse into new stars. So the arms glow blue-white with young, hot, massive stars. Not because those stars formed elsewhere and migrated there, but because the arm is where they were born. They burn bright and fast for a few million years and then explode, seeding the next generation. Our solar system has drifted in and out of spiral arms multiple times over its 4.5 billion year life. We've been in major arms. We've been in the gaps between them. Right now, we're in or near the minor Orion arm. Earlier in our history, we were probably in denser, more active regions. Some researchers have tried to correlate the timing of mass extinction events on Earth with the solar system's passages through the more intense star-forming regions of major arms, places with higher supernova rates, higher cosmic ray flux. The evidence is intriguing, not conclusive. The idea that the structure of our galaxy may have influenced the history of life on Earth is one of those intersections between disciplines that can feel uncomfortable and fascinating at the same time. The stars in the Milky Way are not all the same age. This sounds obvious, but the implication is profound. The galaxy has been forming stars continuously, though at varying rates, for about 13.5 billion years. The oldest stars are nearly as old as the universe itself. The newest stars are being born right now, in dense molecular clouds scattered through the spiral arms, hydrogen collapsing into plasma for the first time, fusion igniting, new suns flickering to life in nurseries of gas and dust. Between those extremes is the entire history of stellar generations in the galaxy, and those generations matter because each successive generation is chemically richer than the last. Here's how it works. The first stars in the universe, and the first stars in the early Milky Way, were composed almost entirely of hydrogen and helium. Those were the only elements that existed. The heavier elements, carbon, oxygen, nitrogen, silicon, iron, calcium, gold, uranium, all of it, did not exist in the early universe. They had to be made. And the only place in the universe that makes them is the cores of stars. In the core of a star like our Sun, hydrogen nuclei are fused into helium. That's the basic reaction that keeps the Sun burning. But in more massive stars, the process goes further. Helium fuses into carbon, carbon fuses into oxygen and neon, eventually into silicon and sulfur, eventually into iron. Each step requires higher temperatures and pressures, but each step also produces energy and creates elements that didn't exist before. iron is the end point. Fusing iron requires energy rather than releasing it. So when an iron core builds up at the center of a massive star, fusion stops. Gravity wins. The core collapses in less than a second. The outer layers fall inward, bounce off the suddenly rigid collapsed core, and are blasted outward in a supernova explosion of almost incomprehensible violence. And in that explosion, in the incredible flux of neutrons during the collapse and bounce, elements heavier than iron get manufactured for the first and only time. Gold, platinum, lead, uranium. All of the heavy elements that require extreme neutron bombardment to build are made in those final seconds of a dying, massive star's life, and then scattered across the galaxy in the supernova shockwave. The star that dies becomes the raw material for the next generation. Our sun is not a first-generation star. It's maybe a third or fourth-generation star. By the time it formed 4.5 billion years ago, the interstellar cloud it formed from had been enriched by multiple previous generations of stellar birth, life, and death. The heavy elements were there because the stars before us put them there. The carbon in every organic molecule in your body was forged in the core of a star that died before our sun was born. The iron in your blood that gives it its red color, that carries oxygen to your cells, was forged in the collapse of a massive star. The calcium in your skeleton, the oxygen in your lungs as you breathe right now. You are made of the nuclear exhaust of stars that died before your planet existed. This is not metaphor. This is chemistry. This is traceable, measurable, verifiable fact. You are star stuff, in the most literal and specific sense that phrase can possibly have. Let's stay with the death of stars for a moment, because it goes further than the supernova. When a massive star collapses and explodes, what's left behind in the center depends on how massive the star was. For stars of a certain mass range, the collapsed core becomes a neutron star, an object with 1 to 2 solar masses compressed into a sphere roughly 20 kilometers across, the size of a city, but with the mass of the sun. The density inside a neutron star is comparable to the density of an atomic nucleus. A teaspoon of neutron star material would weigh about 1 billion tons. Neutron stars often spin rapidly, a consequence of the conservation of angular momentum during the collapse. A stellar core that was rotating once a month speeds up dramatically when it shrinks from a volume millions of kilometers across to a volume 20 kilometers across. The same way an ice skater who pulls their arms in spins faster. The result is a neutron star rotating tens, hundreds, sometimes thousands of times per second. If the neutron star's magnetic field funnels radiation into narrow beams, and if those beams sweep past Earth with each rotation, we detect a regular pulse of radio waves. A pulsar, a cosmic lighthouse. Its beam sweeps through our line of sight once per rotation, like the flash of a lighthouse, regular as clockwork, regular enough in some cases that millisecond pulsars, the fastest rotating ones, keep time with precision that competes with atomic clocks. There are over 3,000 known pulsars in the Milky Way. Each one is the compressed corpse of a dead star, still spinning, still sweeping its beam through the galaxy. Most of them never sweep past Earth at all, their beams aimed permanently in other directions, undetectable, silent from our perspective. The galaxy is full of clocks we can't hear. And then there are the ones that are too massive, even for neutron starhood. If the core that remains after the supernova exceeds roughly 3 solar masses, not even the quantum mechanical pressure that holds neutron star material together against gravity is sufficient. Gravity wins completely. The collapse continues until the object reaches a state that our physics can describe only at the boundary, a singularity, a black hole. Not the black hole at the center of the galaxy. Stellar mass black holes, the remnants of individual dead stars scattered throughout the disk. There are estimated to be 100 million of them in the Milky Way. 100 million stellar remnant black holes drifting through the galaxy, invisible, detectable only when they happen to be orbiting another star, or when they pass in front of a background star, and the bending of light reveals their presence. Most of them are completely silent, invisible, moving through the galaxy in their orbits, carrying the memory of the stars that made them, giving nothing away. The galaxy is full of things we cannot see. More of it is invisible than visible. This is not a minor footnote. The Milky Way has companions, small satellite galaxies, dozens of them, caught in the gravitational pull of the larger structure and orbiting it over timescales of billions of years. Some of them are so diffuse, so sparse, that they were only discovered recently with modern survey telescopes capable of detecting the faint, stellar overdensities they represent. Some of them are dense and old and clearly structured. Some are being torn apart by the tidal forces of the Milky Way even now, their stars strung out into long stellar streams that arc through the galactic halo, debris trails of galaxies being slowly digested. The most famous are the Magellanic Clouds, the Large Magellanic Cloud and the Small Magellanic Cloud. If you're in the southern hemisphere on a dark, clear night, they look like detached pieces of the Milky Way floating near the horizon. Two separate glowing patches, irregular, not the clean spirals of larger galaxies, just bright, irregular accumulations of stars. The Large Magellanic Cloud is about 160,000 light-years away and contains around 30 billion stars. The Small Magellanic Cloud is about 200,000 light-years away, with several billion stars. Both of them are being disrupted by the Milky Way's gravity. A vast stream of gas called the Magellanic Stream extends from the clouds in a great arc across hundreds of degrees of sky, pulled out of those galaxies by tidal forces over hundreds of millions of years. The stream itself is being slowly accreted by the Milky Way, falling into the disk over geological timescales, adding fresh gas for future star formation. Our galaxy is consuming its satellites slowly, the way a large body of water slowly absorbs a smaller one. This is not unique to the Milky Way. Essentially, every large galaxy does this. The Andromeda Galaxy has an extended stellar halo full of streams and shells that are the ghosts of smaller galaxies it has already absorbed. Our own galactic halo contains stellar streams that astronomers have traced back to ancient dwarf galaxies that were disrupted billions of years ago and have been dissolving into the Milky Way ever since. One of the largest of these ancient mergers that the Milky Way absorbed happened roughly 8 to 10 billion years ago. Astronomers have found its signature in the chemical composition and kinematics of stars in the inner galactic halo. A large ancient galaxy, now called Gaia Enceladus, or the Gaia Sausage, merged with the early Milky Way, heating the inner disk, adding billions of stars, and leaving traces that persisted through billions of years of subsequent galactic evolution. Those stars are still identifiable today, billions of years later, by their orbital characteristics, moving through our galaxy like immigrants who arrived long ago, recognizable not by appearance but by how they move. The galaxy carries within it the complete history of everything it has consumed. There is something in the Milky Way that we cannot see, cannot touch, cannot detect directly with any instrument we possess, and yet it outweighs everything we can see by a factor of 5 to 1. Dark matter. The evidence for it in the Milky Way is old and solid and reproducible and has been confirmed by multiple independent methods. The simplest is this. Stars in the outer regions of the galaxy are orbiting too fast. If you calculate how fast those stars should be orbiting based on the gravity of all the visible matter, all the stars and gas and dust that we can account for, you get a number. And then you measure how fast they're actually orbiting. And the actual measurement is systematically, persistently, significantly higher than the prediction. The stars on the outer edges of the galaxy aren't slowing down the way they should. In our solar system, the outer planets move more slowly than the inner ones because they're farther from the sun and the gravitational pull is weaker. The same thing should happen with stars at different distances from the galactic center. The outer ones should be slower. They're not. They're moving at roughly the same speed as stars much closer to the center, as if there's additional mass that we're not seeing providing extra gravitational pull. There is additional mass we're not seeing. The dark matter in the Milky Way forms a roughly spherical halo around the galaxy that extends far beyond the visible disk. The galaxy we can see, all those hundreds of billions of stars, is embedded in a much larger structure of dark matter that we can only infer from its gravity. The total mass of dark matter associated with the Milky Way is estimated to be roughly 10 times the mass of all visible matter combined. We live inside a structure that is 10% visible and 90% unknown. The nature of dark matter remains one of the deepest open questions in physics. It's not ordinary matter in some hidden form. It's not gas we can't see, or black holes, or anything we've been able to account for within the standard model of particle physics. It interacts gravitationally, but not electromagnetically. It doesn't emit light. It doesn't absorb light. It passes through ordinary matter as if it isn't there. It is known only by its effect on the fabric of space and on the orbits of things we can see. The galaxy is mostly made of something we don't understand. Not marginally, mostly. By mass, the overwhelming majority of the Milky Way is dark matter. Everything that glows, every star and nebula and emission region and hot gas cloud that any telescope has ever detected or imaged, all of it together is the minority, the small print. And beyond the dark matter, when you account for the full energy budget of the universe, ordinary matter, atoms, the substance of everything you have ever seen or touched, is only 5% of total content. Dark matter is 27. Dark energy, the even stranger force that appears to be causing the expansion of the universe to accelerate, is 68. We are built from the 5%. We are assembled from the exception. The night sky above your head is a time machine. Not metaphorically. Physically. Light travels at a finite speed. The light reaching your eyes from a star took time to get here. And during that travel time, you have been aging. The Earth has been spinning. Things have been happening. The star you're looking at is not where it appears to be. You're seeing it where it was when the light left it. Not where it is now. The light from the sun takes 8 minutes to reach us. You are always seeing the sun as it was 8 minutes ago. If the sun suddenly vanished, you would not know for 8 minutes. The nearest star beyond the sun, Proxima Centauri, is 4 light years away. The light you see from it left 4 years before it reached your eye. You are looking 4 years into the past. The stars of the Milky Way that are visible to the naked eye are mostly hundreds to thousands of light years away. A star 500 light years distant is showing you itself as it was 500 years ago. When the light from that star left, Columbus hadn't crossed the Atlantic yet. Shakespeare wasn't born yet. The light has been traveling since the middle of the European Middle Ages and just now arrived. The galactic center, 26,000 light years away, is emitting light toward us, right now that will take 26,000 years to arrive. The light we see from that direction tonight left 26,000 years ago, when our ancestors were painting bison and horses on the walls of caves in Europe, when the sea level was lower and you could walk from Europe to Britain, when mammoths still existed. The Andromeda Galaxy, the most distant object visible to the naked eye, shows itself to us as it was 2.5 million years ago. When the light that reaches your eye left Andromeda, the genus Homo had barely begun on Earth. Your direct human ancestors didn't exist yet. Something was there, something that walked upright, but nothing that would recognize what you've become. You cannot see the universe as it is. You can only see the universe as it was, at different ages depending on how far you look. The deeper you look, the younger the universe you're seeing. Modern telescopes routinely image galaxies as they were when the universe was less than 1 billion years old, a fraction of its current age. The most distant detectable objects are showing us the universe in infancy. The sky is a fossil record of light. At the center of the galaxy, very close to Sagittarius A, there is something that shouldn't be there. And the fact that it is there tells us something we didn't expect about the most extreme environment in our galactic neighborhood. There are young, massive, hot stars orbiting the galactic center at very close range, the S-stars as they're called, and they shouldn't exist, or at least they shouldn't be where they are. Here's the problem. Star formation requires the collapse of molecular gas clouds. That collapse happens when gravity within the cloud overcomes the thermal pressure of the gas. But very close to a supermassive black hole, the gravitational tidal forces are so extreme that they tend to shred molecular clouds rather than let them collapse. The same forces that would pull a star apart if it got too close also resist the formation of new stars nearby. Theoretically, the inner regions of the galactic center should be a dead zone for star formation. And yet the S-stars are there, young, hot, unmistakably freshly minted on astronomical timescales. This paradox has driven a significant amount of research. The current best explanation involves stars that may have formed farther out in a disk of gas and then migrated inward through gravitational interactions, or possibly forming in particularly dense, compact clumps of gas that were shielded from tidal disruption long enough to collapse. There is no fully settled answer. What the S-stars have given us, regardless of how they got there, is one of the most precise tests of general relativity ever performed. The star S2, the most famous of them, completes a full orbit around SGR-A in just 16 years. 16 years. Our Sun takes 225 million years. S2 does it in 16. At its closest approach to the black hole, it's moving at about 2.5% of the speed of light. At those speeds, in that gravitational field, the predictions of Einstein's general theory of relativity become measurable and testable. The orbit of S2 precesses, meaning the long axis of its ellipse, rotates over time, and it does so in exact agreement with what general relativity predicts. The shift in color of S2's light as it moves toward and away from the black hole matches relativistic predictions precisely. The gravitational redshift, the stretching of light wavelengths as photons climb out of the intense gravitational well near SGR-A, has been measured directly in S2's spectrum. The center of our own galaxy is confirming the mathematics of space-time, right now, tonight. S2 is somewhere in its 16-year orbit around a 4 million solar mass black hole, moving at thousands of kilometers per second, its light slightly redshifted by the gravitational well it's embedded in, its orbit tracing an ellipse that Einstein's equations predicted would precess, and it does. The universe is telling us the math is right. There are enormous structures in the Milky Way that we didn't know existed until recently. Not small things we missed, enormous things. Structures spanning tens of thousands of light years that somehow escaped detection until we developed the right observational tools. The Fermi bubbles are the most dramatic example. In 2010, the Fermi Gamma Ray Space Telescope revealed 2 enormous lobes of high-energy material extending from the galactic center, one above the plane of the galaxy and one below. Each lobe is roughly 25,000 light-years tall. Together, they span 50,000 light-years, comparable to the radius of the galactic disk. In gamma rays and X-rays, they are enormous, bright, sharply bounded structures rising from the galactic center, like 2 massive exhaled breaths. Invisible light, they're completely invisible. Nobody knew they were there until we looked in the right wavelengths. And once we found them, the question of what made them has dominated galactic center research for 15 years and is still not fully resolved. The leading explanations involve either an ancient period of intense star formation in the inner galaxy, where the combined stellar winds and supernova explosions of massive stars drove vast quantities of hot gas out of the disk, or an episode of activity from Sagittarius A itself, a period when the black hole was actively consuming infalling material at a high rate and driving powerful jets of energy outward. Most researchers think the answer is probably some combination of both, over multiple episodes spanning millions of years. What's striking is not just the scale, though the scale is genuinely staggering. It's the implication that the galactic center has a dynamic history, a history of outbursts and episodes of high-energy activity that has shaped the structure of the galaxy on enormous scales and left physical monuments we're only now detecting. Sagittarius A is relatively quiet right now. By the standards of active galactic nuclei in other galaxies, it is nearly dormant. But it has not always been quiet. The Fermi bubbles are evidence that it has been far more active in the past, and there are X-ray and infrared light echoes in the galactic center region that suggest Escargot was significantly more luminous just hundreds or thousands of years ago, a blink in cosmic time. A quiet black hole is not necessarily a permanently quiet one. The molecular clouds of the Milky Way are where stars are being born right now, and they are extraordinary environments. A molecular cloud is a region of the interstellar medium dense enough and cold enough that hydrogen atoms can pair up into molecules rather than existing as individual atoms. The temperature inside a molecular cloud can fall to 10 degrees above absolute zero, negative 263 degrees Celsius. At those temperatures, gas moves slowly, reaction rates drop, and complex molecules can form on the surfaces of dust grains without being immediately disrupted by thermal energy. And inside molecular clouds, the chemical complexity of the interstellar medium reaches its peak. Astronomers using radio telescopes have detected hundreds of molecules in interstellar clouds, simple ones, carbon monoxide, water, ammonia, and more complex ones, methanol, formaldehyde, formic acid, glycolaldehyde, a simple sugar, amino acid precursors, molecules that, in a warm, wet environment, would be considered pre-biological. The building blocks of the chemistry of life are scattered throughout the molecular clouds of the Milky Way. Not life itself, not cells, not anything self-replicating, but the raw organic chemistry that, given the right environment, given warmth and liquid water and time, can begin the long process of organization into something more complex. This is not speculative. This is observational data from radio telescope surveys. The galaxy is full of organic molecules. The question is not whether the ingredients exist. The question is how often the right recipe gets assembled under the right conditions. The Orion molecular cloud is the most intensively studied star-forming region near us, about 1,300 light-years away. Embedded within it is the Orion Nebula, the fuzzy star in the middle of Orion's sword that you can resolve as a cloud with the naked eye on a dark night. The nebula is a cavity blown into the molecular cloud by the fierce ultraviolet radiation of young massive stars that formed there less than 1 million years ago. The radiation from those newborns is ionizing the surrounding gas and making it glow pink and red in ways that are invisible to the eye but spectacular in long-exposure photographs. Deeper within the molecular cloud, further from the young massive stars, the cooler, denser cores are still collapsing. Still forming new stars right now. Stars that will take another 1 million or more years to ignite. Stars that don't exist yet, but will. The galaxy is not a finished product. It is a process. There is a moment in every consideration of the Milky Way where the individual facts give way to something harder to name. All of this complexity, all of this history, all of these structures from bare Fermi bubbles spanning 50,000 light-years to ESSI stars orbiting at 2.5% of the speed of light to molecular clouds making sugar in the dark at 260 degrees below zero, all of it assembled from nothing more complicated then hydrogen, helium, time, and gravity. The universe started with two elements, hydrogen and helium. That's it. Everything else is secondary production. Everything heavier than helium on the periodic table was made by stars, in stellar cores, in supernova explosions, in the collision and merger of neutron stars. The universe gave the galaxy a kit with only two pieces and then left it alone for 13 billion years, and it made this. 200 billion stars. Billions of planetary systems. A dark matter halo 5 times more massive than everything you can see. Spiral arms as density waves propagating through the disk. Molecular clouds seeding new stars with pre-biological chemistry. A 4 million solar mass black hole at the center, whose event horizon shadow we have now photographed. 50,000 light-year Fermi bubbles we didn't know about until 2010. 100 million stellar mass black holes moving invisibly through the disk. Thousands of spinning neutron star lighthouses sweeping their beams through the galaxy. Ancient dwarf galaxies dissolved into the halo. A stellar stream from the Sagittarius dwarf galaxy arching through the sky. The Magellanic clouds in slow gravitational dissolution, trailing a stream of gas that stretches across half the southern sky. All from hydrogen, helium, and gravity. And in one small spiral arm, 26,000 light-years from the center, one of those billions of planetary systems contains a rocky planet. Third from its star, 4.5 billion years old. And on that planet, one of the things that the galaxy assembled from its elements developed enough complexity to look up at the pale smear of light across the night sky and ask what it was, and began to find out. The question that never entirely goes away when you spend time with the Milky Way is whether it contains other minds asking the same questions. We don't know. That's the honest starting point. We genuinely, frustratingly, profoundly do not know. And the uncertainty cuts in two directions simultaneously, which is what makes it genuinely interesting rather than just uncomfortable. On one side, the galaxy is enormous and old. 200 billion stars, many of them with planets. The sun has been around for 4.5 billion years, and the galaxy is 3 times older than that, meaning there was time enough for solar-type stars to form and produce life long before Earth existed. If life arises wherever conditions allow it, if the transition from chemistry to biology is a natural output of the right environment given enough time, the galaxy could be full of it. There could be civilizations billions of years older than ours. There could be things that have been asking questions about the galaxy for longer than multicellular life has existed on Earth. On the other side, we've been looking and listening for a long time and haven't found anything. Radio telescopes have been scanning the sky for artificial signals since 1960. We've searched thousands of stars at multiple frequency ranges. We've found nothing that wasn't explainable by natural processes. The galaxy, so far, appears to be sending us nothing in the way of unambiguous artificial signals. This absence is data. It doesn't prove solitude, but it constrains the possibilities. The paradox has a name. Fermi's paradox, after the physicist Enrico Fermi, who asked the question at lunch in 1950. Something along the lines of, if the galaxy is full of civilizations, where is everybody? A galaxy this old, if it contains technological civilizations that develop the motivation to expand or communicate, should show some sign of that activity. And it doesn't, or at least not to our current level of detection. The explanations for this range from deeply sobering to strangely hopeful. Maybe the transition from chemistry to life is extraordinarily rare, and we are essentially alone. Maybe the transition from life to complex multicellular life is the bottleneck. Maybe the transition from complex life to technological civilization is rare. Maybe technological civilizations tend to destroy themselves before they can become detectable. Maybe they become detectable, but communicate in ways we haven't learned to recognize yet. Maybe the galaxy is full of signals we're not receiving, because we're not looking at the right frequencies, or we lack the interpretive framework to recognize the signal as artificial. Or maybe the galaxy is quiet, for the same reason that this document can tell you so much about it. We are early. The average star in the Milky Way is older than our Sun, but the conditions for rocky planet formation with the right chemistry weren't fully in place in the earliest eras of the galaxy. Life might only really get started in earnest in the middle and later eras of galactic history, in which case we might be among the first technological civilizations to emerge. Not alone, but early. The most profound implication of that possibility is that whatever the Milky Way becomes, in terms of conscious observation and understanding of itself, we might be among its first instruments for self-knowledge. A galaxy that has been here for 13.5 billion years might be, right now, in the first moments of becoming aware of itself through the minds it has generated. There's a calculation that changes everything once you've done it. Compress the entire history of the Milky Way into a single calendar year. January 1st, midnight, is the formation of the galaxy about 13.5 billion years ago. Every day in this calendar year represents roughly 37 million real years. The oldest stars in the halo form in January. The disk begins to build through late winter. The spiral structure organizes through spring and summer. Our Sun forms around September 9th. Life appears on Earth in mid-September. The oceans form, chemistry starts. Single-celled life gets going through the rest of September, October, November. Through all of that, nothing on Earth that you could identify. Just microbial mats, just chemistry experimenting with complexity in the dark oceans. The first multicellular organisms appear around mid-November. The Cambrian explosion, the sudden flowering of complex animal life, is around December 14th. Dinosaurs appear on December 26th. The asteroid hits on December 30th. Mammals diversify and diversify and diversify through December 31st. Primates appear. Great apes, hominids, Homo sapiens, our species, emerges on December 31st at about 11:38 in the evening. The pyramids were built at 11:59 and 55 seconds. Everything after that, the Roman Empire, the invention of printing, the scientific revolution, the industrial revolution, the discovery of electricity, the development of radio, the moon landing, the internet, everything that human civilization has accomplished, and everything you personally have ever experienced or will experience, all of that happens in the last 5 seconds of December 31st. 5 seconds. You are standing at the very leading edge of the last 5 seconds of the galactic year, the earliest moment when something has been present to see what the galaxy looks like. Whatever comes next in galactic history, whatever the Milky Way does in its second cosmic year, and its third and its 100th, it begins in the seconds immediately after now. The fate of the Milky Way involves a merger. The Andromeda Galaxy, 2.5 million light-years away, is not moving away from us the way most galaxies are in our expanding universe. It's moving toward us. The mutual gravitational attraction between the two largest members of the local group has overcome the expansion of space between them. Andromeda is approaching at roughly 110 kilometers per second, and in approximately 4 to 5 billion years, the two galaxies will collide. Collision is a slightly misleading word. The stars within each galaxy are so vastly separated from each other that when two galaxies interpenetrate, the probability of any two individual stars actually hitting each other is essentially negligible. What happens is a gravitational event, not a physical impact. Stars will be flung onto radically different orbits by the combined gravitational fields. The spiral structures of both galaxies will be disrupted. The galaxies will pass through each other, swing out, fall back together, pass through each other again, and over hundreds of millions of years of this orbital dance, eventually merge into a single structure. Probably an elliptical galaxy. No longer a disk, no longer spiral. A more chaotic, pressure-supported structure of stars in randomized orbits, the end product of two spinning disks being scrambled by repeated gravitational interactions. Our Sun will almost certainly survive this. The probability that the Sun encounters another star closely enough to be disrupted is small. The solar system will probably persist, but the night sky in those billions of years will be unlike anything visible today. The galaxy will be filling the sky, the two disks interacting, the sky alight with new star formation, triggered by the gas compression of the merger, then gradually quieting as the gas is consumed and the merged galaxy settles into old age. 4 billion years from now, the Sun will also be aging, approaching the end of its hydrogen fuel, swelling into a red giant. The inner solar system will become hostile long before the Andromeda merger is complete. These two processes, the merger and the Sun's evolution, will overlap in a way that makes the long-term future of Earth genuinely complicated. But these are 4 billion-year problems. The Milky Way as it exists tonight, with its spiral arms and its central bar and its molecular clouds and its S-stars and its Fermi bubbles and its dark matter halo, will persist in roughly this form for billions of years. It will be recognizably the same structure for longer than it would take another observer at our level of intelligence to evolve from scratch somewhere else in the galaxy, given what we know about evolutionary timescales. The galaxy you're inside tonight is durable. It has time. Let's go back to the beginning one more time. The Milky Way formed when the universe was about 200 million to 1 billion years old. Before that, the universe was a hot, dense soup of radiation and simple matter, hydrogen and helium gas. As the universe expanded and cooled, gravity began to do its work. Regions of the early universe that were slightly denser than average attracted more matter. Matter fell toward those dense regions. Sheets and filaments of matter assembled. Gas began to collapse. The first stars formed in those early dense regions. They were enormous by the standards of today's stars, made entirely of hydrogen and helium, no metals, no carbon, no oxygen, to provide the additional cooling mechanisms that allow smaller stars to form. They were probably hundreds of times more massive than our Sun, and they burned through their fuel in just a few million years and exploded, seeding the early universe with the first heavy elements. Those explosions enriched the surrounding gas. The next generation of stars had a slightly more complex chemistry, and so on, generation after generation, the interstellar medium becoming progressively richer in elements heavier than helium. The process that led to you being here, made of carbon and oxygen and iron and nitrogen, required that several generations of stars be born, live and die before the material existed to assemble you. The Milky Way, in its earliest form, was a chaotic, irregular assemblage of gas and the remnants of these early stellar explosions. Over billions of years it organized, the disk formed, the bar assembled, the spiral structure developed, satellite galaxies were consumed and absorbed, the halo built up its population of ancient globular clusters. Gradually, over 8 or 9 billion years of evolution, before the Sun even formed, the galaxy became the structure that then gave rise to our solar system. And the solar system formed, and 4.5 billion years passed, and now something in it is lying in the dark and thinking about all of this. That's where you come in. There's a specific number that tends to end conversations when you say it out loud. If you could tag every atom in your body and wait, most of those atoms have a history in the Milky Way, stretching back billions of years. The hydrogen in your body, and your body is about 60% water, which is 2/3 hydrogen, has been around since shortly after the Big Bang. It's 13.5 billion years old. It was in the interstellar medium. It was part of molecular clouds. It was briefly inside other stars. It was in the cloud that collapsed to form the Sun. It was in the protoplanetary disk. It was in comets and asteroids. Some of it fell to Earth in those early bombardment eras. Some of it was incorporated into the first oceans. It has been cycling through the biosphere for billions of years, through billions of other organisms. The hydrogen in the water in your body right now was in the ocean during the age of dinosaurs. It was in the clouds when the Cambrian explosion filled the seas with complex animal life. It was in the molecular cloud of the nebula that collapsed into our solar system 4.5 billion years ago. It was drifting in the early Milky Way for billions of years before that. And here it is, right now, organized, temporarily, into you, participating in the electrochemical activity of a nervous system, carrying signals between cells, part of the water that your blood cells use to carry oxygen, part of the fluid in your eyes that lets you read, part of every breath. The atoms don't know this. They don't have experience. They're not aware of having been in a dinosaur or in a molecular cloud. But you are. You can know the whole chain. You can trace the lineage from the Big Bang, through stellar nucleosynthesis, through supernova dispersal, through molecular cloud chemistry, through solar system formation, through planetary geology, through biological evolution, through human consciousness, to this specific moment, this specific awareness of the full sequence. That awareness is, as far as we know, new in the history of the galaxy. Nothing in the first 13 billion years of the Milky Way's history had the capacity to look at the galaxy and understand what it was looking at. That capacity arose in the last 5 seconds of the galactic year. Maybe it arose elsewhere, too, in other solar systems, around other stars. Maybe it arose first elsewhere. We don't know. What we know is that it arose. The galaxy made something that can see it, something that can map its spiral arms and photograph its central black hole and detect the gravitational waves from neutron star mergers 100 million light-years away and determine the age of its oldest stars and trace the chemical evolution from hydrogen to human. The galaxy is looking at itself, through you, through every human who has ever stood under a dark sky and tilted their head back and watched the pale river of light and wondered what it was. That's not nothing. That's actually the most astonishing thing in all of this. The Milky Way. Right now, tonight, as you settle into the dark, is doing everything it always does. In a molecular cloud in the Orion Arm, a cold, dense core of gas and dust is reaching the threshold of gravitational collapse. In the next 1,000,000 years, it will become a star. There may be planets. Tonight it is still gas, still cold, still potential. 300 light-years away, a white dwarf, the cooling remnant of a star similar to our sun that died 1 billion years ago, is drifting through the disk in perfect silence. It is the size of Earth and the mass of the sun, and it glows faintly in the dark, cooling toward absolute zero on a timescale of trillions of years. 20 light-years from Earth, a red dwarf star is orbited by several planets. It has been burning for 12 billion years and has billions more to go. On one of those planets, the conditions might be there. Liquid water, organic chemistry, the right temperature range. We don't know. We haven't looked closely enough yet. Maybe there's nothing. Maybe there's something. Maybe there's everything. At the galactic center, Sagittarius AA is in its current relatively quiet state, but the stars orbiting it are continuing their paths. S2 is somewhere in its 16-year ellipse, moving at thousands of kilometers per second, its orbit tracing the mathematics of space-time. The orange ring of glowing gas surrounding the black hole's event horizon is still there, still emitting, still sending photons in all directions, some of which will reach Earth in 26,000 years. The Fermi bubbles are still there, still visible in gamma rays if you know where to point. Still 50,000 light-years of superheated material rising from the galactic center in structures we didn't know existed 15 years ago. The large Magellanic Cloud is still orbiting, still trailing its stream of gas, still gradually being drawn closer. In 1 billion years, the tidal disruption will be further along. In tens of billions of years, it will be gone, absorbed into the Milky Way. Andromeda is still approaching, 4 billion years away from us at present velocities. The night sky looks the same, tonight as it did last night, will look the same tomorrow. The change is real, but it requires a billion-year perspective to notice. And the dark matter halo is still there, silent and invisible and dominant, holding the galaxy together with a gravity we can measure and a nature we don't understand. All of this is happening right now, tonight, in the galaxy you're inside. The pale river of light, if you could see it tonight on a perfectly dark horizon, hangs there with a patience that makes the word ancient feel inadequate. It does not care about your questions. It does not know you're asking them. It is not providing answers on purpose. It's a collection of 200 billion nuclear furnaces and their associated debris and the dark matter that holds them together, doing what gravity and physics dictate, the same tonight as it was 3 billion years ago. And yet, it made you. Not you specifically, not with intention, but the process that produced you ran inside this structure. Every atom in your body was processed through multiple stellar generations within this galaxy before it was assembled into something that could look up at the source and recognize, with appropriate awe and appropriate humility, what was looking back. You are made of the Milky Way. You are not looking at it from outside. You are not a spectator. You are a participant, a temporary local organization of its matter, a brief eddy of complexity in 13.5 billion years of stellar evolution that for a few decades in the 5-second final moment of the galactic year gets to be aware of the whole thing. The stars don't need you to understand them to continue burning. The galaxy doesn't require your awe to keep its spiral arms in motion. The dark matter is indifferent to your curiosity about it. But you get to be curious anyway. That's what the last 5 seconds produced. The galaxy made something that can look at the galaxy. Lie here in the dark with that for a while. The river of light is still there, even when you can't see it. It will be there tomorrow. It will be there long after the last person who remembers tonight is gone. The stars don't need the watching to keep burning. But it is good to watch them. It is good to know where you are. You are inside the Milky Way, and it is extraordinary. Let's go back to something that gets glossed over in almost every explanation of the galaxy. The spiral arms are beautiful. Everyone agrees on this. The photographs from space telescopes of other galaxies showing their elegant curved arms lit up in blue and pink, the massive young stars blazing in the arms, the reddish clouds of ionized hydrogen marking the star-forming regions. Beautiful, clear, iconic. But when you actually think about the physics of why those arms exist, why they persist, why they have the specific shape they do, you enter territory that is significantly stranger than the photographs suggest. A spiral arm, as we said, is a density wave, a compression pattern propagating through the disk. But what drives the pattern in the first place? What started it? And what keeps it going for billions of years rather than smearing out into a uniform disk? This is actually an unresolved problem in astrophysics. Seriously, the origin and maintenance of spiral structure in galaxies is not a closed question. There are competing theories. The most widely accepted framework is the density wave theory developed by C.C. Lin and Frank Hsu in the 1960s, which treats the spiral as a standing wave pattern in the rotating disk, somewhat analogous to the wave pattern that forms in a flowing river around an obstruction. But this theory has difficulties explaining all the observed varieties of spiral structure in different galaxies, and the mechanisms by which the spiral is maintained against dissipation are still debated. Alternative explanations include swing amplification, a process by which shearing motions in the rotating disk can amplify and regenerate spiral structure from random perturbations. There's also the role of bars and other non-axisymmetric features in driving spiral structure. And there's the contribution of dark matter, whose distribution affects the gravitational potential through which the disk rotates and therefore influences what wave patterns can be sustained. The Milky Way's spiral structure is particularly hard to work out because we're inside it, Mapping our own galaxy's arm structure has been one of the long-running projects of radio astronomy, using the emission of cold hydrogen gas at a wavelength of 21 centimeters to trace the distribution of gas across the disk. The result, built up over decades, is a map that shows the general spiral structure, but with significant uncertainties, particularly on the far side of the galaxy, where the view is most obscured and the distance measurements are least precise. The Gaia satellite, launched by the European Space Agency, has been transforming this picture. By measuring the positions and motions of over 1 billion stars with extraordinary precision, Gaia is giving us something we've never had before, a three-dimensional map of the galaxy's stellar population, with enough accuracy to actually see the structure of the disk. Not inferred from indirect measurements. Directly measured, star by star, their positions in 3 dimensions and their velocities through space. What Gaia has shown is a galaxy more complicated than the simple textbook diagrams suggest. The disk is not flat. It warps and flares in the outer regions, curling up on one side and down on the other like the brim of a hat that's been pushed unevenly. This warp is real and has been known for decades from radio surveys, but Gaia has mapped it in stellar positions with unprecedented precision. Something is causing the outer disk to be distorted, possibly the gravitational influence of the Magellanic Clouds, possibly the asymmetric distribution of dark matter in the halo, possibly both. There are also ripples in the disk, structures that look like the surface of a lake disturbed by a pebble, concentric rings of slightly higher and lower stellar density propagating outward through the plane of the galaxy. These might be the remnants of ancient impacts of satellite galaxies passing through the disk, or they might be resonant structures driven by the gravitational bar at the center, or they might be something else entirely. The Milky Way is not the smooth, clean, idealized disk of the textbook diagrams. It is a complex, warped, rippled, asymmetric, actively evolving structure with more detail and more mystery than most people imagine. The interstellar medium deserves more attention than it usually gets. It tends to be described as the stuff between the stars, which is technically accurate but makes it sound like empty space with a little gas mixed in. That undersells it significantly. The interstellar medium, the ISM, is a complex, multi-phase environment. It exists simultaneously in several distinct phases, from cold, dense molecular clouds where temperatures hover near absolute zero, to warm, neutral hydrogen gas at thousands of degrees, to warm ionized gas at 10,000 degrees, to hot diffuse plasma at millions of degrees. These phases coexist throughout the galactic disk, constantly being stirred and heated and cooled by the energy inputs from stars. The hot phase, the million-degree plasma, is maintained primarily by supernova explosions. A supernova blasts a bubble of superhot gas into the ISM. The shock wave heats everything it touches. Then the bubble expands and cools. Multiple supernova remnants overlapping create a network of hot cavities in the ISM, collectively called the hot interstellar medium, or the local bubble of the ISM. We actually live inside one of these bubbles. The local bubble is a region of relatively low density and hot gas, about 1,000 light-years across, created by a series of supernovae over the past few million to tens of millions of years. The solar system sits near the center of this bubble. The gas density immediately around us is lower than the average ISM density, the result of those ancient explosions clearing out the surrounding material. The nearest molecular cloud complexes, the nearest dense, cold, star-forming regions, are at the edge of the local bubble. We can see them in the night sky as dark patches where the dust absorbs background starlight. The coal sack, visible from the southern hemisphere, is one. The dust lanes in Cygnus are another. These dark silhouettes are the walls of the local bubble, the cold, dense molecular material at the boundary of the hot cavity we inhabit. A few million years ago, several massive stars in our neighborhood exploded. Those explosions created the bubble we now live in, and may have left their mark in geological records on Earth. Iron-60, a radioactive isotope that is produced in supernovae, has been found in elevated concentrations in deep-sea sediments and in lunar samples at depths corresponding to material deposited roughly 2 to 3 million years ago, the same era when early hominids were first appearing on Earth. The Milky Way was active in our neighborhood at the dawn of human evolution. Whether the supernova radiation at that time influenced the course of biological evolution in any meaningful way is not known, but the coincidence of timing is noted. Let's talk about a specific type of star that most people underestimate severely. Red dwarfs, M-type stars, are the most common type of star in the Milky Way by an enormous margin. They make up roughly 70 to 75% of all stars in the galaxy. Every 3 out of 4 stars is a red dwarf. Our immediate neighborhood of stars is dominated by them. Proxima Centauri, the closest star to the Sun, is a red dwarf. Barnard's star, the second nearest, is a red dwarf. Of the 40 or so nearest stellar systems to the Sun, the majority contain red dwarfs. They are small. The smallest red dwarfs are about 8% of the Sun's mass, just barely above the threshold for nuclear fusion to ignite, so close to the edge that if you removed a small amount of material, they'd be brown dwarfs instead, objects that glow with residual heat but can't sustain fusion. The largest red dwarfs are about 60% of the Sun's mass. Their surfaces are much cooler than the Sun, not the white-yellow color of our star, but deep orange to red. Their luminosity is a tiny fraction of the Sun's. Proxima Centauri is about a 1/1500th of the Sun's luminosity, but they are extraordinarily long-lived. A star's lifetime is determined by how quickly it burns through its hydrogen fuel. Our Sun, which is much more luminous than red dwarfs, is burning through its fuel at a rate that gives it a total lifespan of roughly 10 billion years. Red dwarfs, burning much more slowly, can last from tens of billions to trillions of years. The smallest red dwarfs have calculated main sequence lifetimes longer than the current age of the universe. The universe is not yet old enough for any red dwarf to have run out of hydrogen fuel and died. Every red dwarf that has ever formed is still alive. This has an interesting implication for the future distribution of life in the galaxy, if life exists elsewhere. The red dwarfs that formed early in the galaxy's history have had billions of years more than the Sun's planets to develop potential life, and they'll continue to provide stable environments for trillions of years after the Sun has swollen into a red giant and rendered Earth uninhabitable. In terms of sheer time available for biology, red dwarfs vastly outcompete stars like the Sun. If life is common in the galaxy, and particularly if it's common around red dwarfs, then the vast majority of life in the long-term future of the galaxy will be huddled around these dim, patient, ancient stars. The challenges for life around red dwarfs are real. The habitable zone is close in because the star is dim. Planets in the habitable zone are likely tidally locked, presenting one face permanently toward the star. The star flares, sometimes violently, exposing close-in planets to doses of ultraviolet and X-ray radiation that would be sterilizing on Earth's unprotected surface. But these are engineering problems for biology, not necessarily absolute barriers. The history of life on Earth is a history of adaptation to seemingly hostile conditions. Life in the deep ocean near hydrothermal vents. Life in hypersaline lakes. Life in the stratosphere. Life in the dry valleys of Antarctica. Life seems to go where chemistry allows, and sometimes where you wouldn't think chemistry would allow. The nearest example, Proxima b, orbits Proxima Centauri in its habitable zone. It was discovered in 2016. It's 4 light-years away. If there is life at Proxima b, something is alive 4 light-years from Earth right now. Something lives around the nearest star. Something is there, potentially, in the dark, in its tidally locked permanent day and night, around a dim red star that has been burning for longer than Earth has existed? We don't know. But we could conceivably find out within this century. Not by sending people, that's still far beyond current propulsion technology, but by watching the planet's atmosphere carefully when it transits in front of its star, looking for the chemical signatures that living processes leave in an atmosphere. Oxygen, methane, ozone, combinations that don't persist without biological replenishment in the conditions we understand. 4 light years, the nearest possible answer to whether we're alone. The globular clusters of the Milky Way are relics. There are about 150 to 200 of them orbiting the galaxy in its halo, enormous spherical clusters containing hundreds of thousands to millions of stars, packed into regions only a few dozen to 100 light-years across. They are among the oldest structures in the galaxy. Some of them are 13 billion years old, nearly as old as the universe itself. The density of stars inside a globular cluster is extraordinary by the standards of the galactic disk. Near the centers of the most compact clusters, stars are separated by a fraction of a light-year. In our neighborhood of the galaxy, the nearest star is 4 light-years away. In the core of a dense globular cluster, the equivalent separation might be 1/10 of that. The night sky from a planet inside a globular cluster would be unrecognizable. Instead of a handful of bright stars visible to the naked eye, there would be millions, the sky never fully dark, the collective light of the cluster providing something like permanent starlight. The stars inside globular clusters are old and metal-poor. They formed in the first billion years of the galaxy's life, before multiple generations of stellar evolution had enriched the interstellar medium with heavy elements. Their chemistry is primitive by the standards of stars like the Sun. They're mostly hydrogen and helium, with just traces of heavier elements. This chemical poverty has implications for the possibility of life inside globular clusters. Rocky planets require rock, which means silicon and oxygen and iron, elements that are scarce in the earliest stellar generations. Planets around globular cluster stars would likely be small and rocky, with much less of the chemical complexity that Earth-based life uses. Whether life could arise in those conditions, with a reduced chemical palette, is genuinely uncertain. It might. Earth life uses a subset of all available chemistry. A different subset might support a different kind of life. What makes globular clusters additionally interesting from an astronomical perspective is their dynamics. With hundreds of thousands of stars packed into a volume only a few dozen light-years across, close encounters between stars are common on astronomical timescales. Stars can exchange companions in binary systems. Stars can be flung onto new orbits by gravitational interactions. In the densest cluster cores, stellar collisions can actually occur, 2 stars merging into a single more massive star, creating what are called blue straggler stars, objects that are bluer and hotter than expected, given the age of the cluster, as if they've found a way to stay young in a very old population. These ancient spherical cities of stars, each one orbiting the Milky Way in its own slow path through the halo, are the oldest unchanged structures in the galaxy. They have been there since nearly the beginning. They will be there long after the disk has been disrupted by the Andromeda merger, their dense stellar cores too tightly bound to be easily disrupted by galactic collisions. One of the stranger things astronomy has discovered about the Milky Way is that it has a magnetic field. Not a strong one. Not strong in the way that a bar magnet or even the Earth's magnetic field is strong. But it is real, it is measurable, and it is enormous. The galactic magnetic field threads through the spiral arms and the disk, organized partly along the direction of the arms, with a complex structure that varies from region to region of the galaxy. The field strength in the disk is a few microgauss, roughly 1,000,000 times weaker than a typical refrigerator magnet. But it pervades a volume of space so immense that its total energy content is significant, and it has consequences that reach across galactic scales. Cosmic rays, high-energy charged particles moving through the galaxy at near the speed of light, are affected by the galactic magnetic field. When a charged particle moves through a magnetic field, it spirals along the field lines rather than traveling in a straight line. The magnetic field causes the cosmic rays to wander through the galaxy, bouncing and spiraling, and taking much longer to escape than they would without the field. This confinement of cosmic rays by the galactic magnetic field has consequences for the energy density of cosmic rays throughout the disk, for the heating of the interstellar medium, for the pressure balance that determines where gas can collapse to form stars and where it remains diffuse. The origin of the galactic magnetic field is itself a research frontier. The current understanding involves something called the galactic dynamo, a mechanism by which the differential rotation of the galaxy, the way different parts of the disk orbit at different angular rates, combined with the turbulence stirred up by supernovae and stellar feedback, can amplify and organize a seed magnetic field into the large-scale coherent structure we observe. The same basic principle operates inside stars and planets, converting kinetic energy of rotation and convection into magnetic field energy. But the detailed physics of the galactic dynamo and why the field has the specific structure it does are still active research questions. We can measure the field through its effects on radio emission from the galaxy, through the polarization of light from background stars, through the rotation of the plane of polarization of radio waves as they travel through the magnetized plasma of the ISM. The measurements constrain the models. The models are still being refined. The galaxy is threaded with magnetic field that shaped how it evolved and how it continues to evolve. Another invisible structure, another layer of physical reality that doesn't show up in the photographs, but is woven through the entire galaxy. There is a way of thinking about the Milky Way's chemical evolution that makes the periodic table feel like a narrative. Hydrogen was first. All the hydrogen that exists today was produced in the first few minutes after the Big Bang. The universe, shortly after its origin, was hot enough for nuclear reactions, and in those first minutes it fused some hydrogen into helium and a trace of helium into lithium. And then the universe cooled and expanded, and the conditions for those reactions ended. And that was it. For the first few 100 million years, just hydrogen, just helium, a trace of lithium, nothing else. Then the first stars formed. In their cores, under the crushing pressure of gravity, hydrogen fused into helium. Energy radiated out. The stars shone, and in the most massive of them, when the hydrogen ran low, helium began to fuse into carbon. Carbon fused with helium to make oxygen. Oxygen fused to make neon, then sodium, then magnesium, silicon, sulfur, and finally iron. And when iron built up in the core, fusion stopped and the star collapsed. In the seconds of that collapse, in the neutron flux of the supernova explosion, elements heavier than iron formed for the first time. Gold, silver, platinum, iodine. The heavy end of the periodic table, assembled in the dying moment of a massive star. That star's material spread through the surrounding galaxy, found its way into new molecular clouds, seeded those clouds with the full periodic table for the first time. The next generation of stars that formed from those clouds were chemically richer. They could build rocky planets with iron cores and silicate mantles. They could have oceans. They could have chemistry of sufficient complexity to eventually produce organic molecules in warm pools and hydrothermal vents. Each stellar generation enriched the galaxy's interstellar medium further. The Milky Way today, nearly 14 billion years into this process, has an interstellar medium that contains the full periodic table. Not uniformly, not everywhere in the same proportions, but present. The outer disk is less enriched than the inner disk. The halo is less enriched than the disk. The young star-forming regions are the most enriched of all, accumulating the output of the most stellar generations. The periodic table is a map of cosmic time. The light elements, hydrogen and helium and lithium, are ancient, dating to the first minutes of the universe. The medium elements, carbon through iron, were built up over billions of years of stellar evolution. The heavy elements, gold and platinum and uranium, required specific violent environments, supernovae and neutron star mergers to assemble. Each element on the table carries the signature of how it was made and when. When you look at a periodic table, you're not looking at a chemistry reference. You're looking at a compressed history of 13.5 billion years of stellar evolution in the Milky Way and the universe before it. Every row is a chapter. Gravitational waves are a new way of listening to the galaxy. Einstein's general theory of relativity predicts that accelerating massive objects should create ripples in the fabric of space-time, waves that propagate at the speed of light, compressing and stretching space itself as they pass. These gravitational waves were predicted in 1916. They were finally detected directly for the first time in 2015 by the LIGO detectors in the United States. The first detection was the merger of two black holes, each about 30 solar masses, about 1.3 billion light-years away. The merger lasted a fraction of a second at its peak. In that fraction of a second, it radiated more energy in gravitational waves than the entire visible universe radiates in electromagnetic radiation, in all forms of light, in that same fraction of a second. And the ripple from that event traveled for over 1 billion years and arrived at Earth in 2015 and compressed and stretched the LIGO detectors by a distance smaller than 1,000th the diameter of a proton. We detected that. We built an instrument sensitive enough to detect space-time distortions 1,000 times smaller than an atomic nucleus. Since that first detection, dozens of gravitational wave events have been observed. Binary black hole mergers, binary neutron star mergers, possible neutron star black hole mergers, each one an event somewhere in the universe where two compact objects spiraled together and merged in a burst of gravitational wave emission and electromagnetic radiation. The binary neutron star merger, GW-70817, detected in 2017, was observed simultaneously in gravitational waves and in light across the full electromagnetic spectrum from gamma rays to radio. It confirmed that neutron star mergers produce the heavy elements, the gold and platinum and other R process elements. It confirmed that gravitational waves travel at the speed of light. It opened the era of multi-messenger astronomy, where the same event is observed with multiple completely different types of signals simultaneously. Within the Milky Way, gravitational waves from merging compact objects should in principle be detectable, but they haven't been caught in the act yet. Most of the known events have been in other galaxies. However, the Milky Way certainly contains binary systems of neutron stars and black holes that will eventually merge, some perhaps in geologically near future in cosmic terms. When the next generation of gravitational wave detectors comes online, with greater sensitivity, the merger rate detectable within our own galaxy should increase. There may also be a stochastic gravitational wave background, a hiss of gravitational waves from all the mergers throughout cosmic history, accumulating into a background noise that permeates all of space. Pulsar timing arrays, which use the extraordinary precision of millisecond pulsars as clocks to detect tiny variations in the pulse arrival times caused by gravitational waves passing through the galaxy, have recently found evidence for exactly such a background. The Milky Way's pulsars are humming in response to the gravitational wave background of the universe. The galaxy is vibrating in waves we're just beginning to hear. There's a structure in our galactic neighborhood called the local sheet that places the Milky Way in an immediate cosmic context worth understanding. The local group, our cluster of galaxies including the Milky Way, Andromeda, and their attendant dwarf galaxies, is not floating in isolation. It sits in a plane of galaxies called the local sheet, a roughly flat arrangement of nearby galaxy groups spanning about 7 million light-years. The Milky Way, Andromeda, the Maffei group, the Sculptor group, the Centauri group, all the nearby galaxy concentrations, tend to lie in or near this plane. The flat arrangement is not perfect and not sharp, but it's real and it has a cause. The cause is the way the cosmic web organized matter. The filaments of the cosmic web are planar in their local geometry. Matter accumulates into sheets and filaments rather than spherical clumps. The local sheet is a sheet in the cosmic web, a region where matter gathered during the universe's early evolution, and the galaxy groups within it are the dense nodes that formed within that sheet. Beyond the local sheet, in the direction perpendicular to the plane, there are the cosmic voids. The local void is a large underdense region adjacent to the local group, a vast expanse where the density of galaxies is far lower than average. The Milky Way is being pushed slightly away from the local void as the overdense regions around us, including the Great Attractor in the direction of Centaurus, pull us toward them. We are falling in multiple directions simultaneously, away from voids and toward concentrations in the grand drama of cosmic structure formation. The local sheet is itself falling toward the Virgo cluster, the nearest large galaxy cluster, about 53 million light-years away in the direction of the constellation Virgo. The Virgo cluster contains about 1,000 galaxies and has a total mass of roughly 10,000 times the mass of the Milky Way. Its gravity is enough to influence the local flow of galaxies in our region of space. Everything at every scale is in motion. Every structure is falling towards something. The hierarchy goes from planets orbiting stars to stars orbiting the galactic center, to the Milky Way falling with the local group toward Andromeda, while both fall toward the Virgo supercluster, while all of that falls toward the Great Attractor, while all of that participates in the large-scale flow of matter through the cosmic web. You are at the bottom of this hierarchy of motion, on a rocky planet, orbiting a star, orbiting a galaxy, orbiting nothing, just participating in the general flow. And the general flow is toward structure, toward concentration, toward the great attractor of mass that the universe has been building since the Big Bang. There is something worth saying about the night sky that often gets left out. The Milky Way's visibility from Earth changes across the year in a regular, predictable, beautiful way. This is not because the galaxy moves. The galaxy doesn't orbit Earth. It's because Earth orbits the Sun. And as we move around the Sun over 12 months, the direction we face on the night side of the planet changes, giving us a rotating window onto different parts of the surrounding sky. In the northern hemisphere, the galactic center in Sagittarius is most visible in summer, particularly July and August. The evenings of midsummer are when the thickest, brightest part of the galactic band is overhead in the pre-dawn darkness or high in the sky after midnight. This is when observers in dark locations see the full splendor of the Milky Way, the complex central region with its dust lanes and brighter star clouds, the nuclear bulge glowing softly above the southern horizon. In winter in the northern hemisphere, the galaxy is still there, but you're looking away from the center, toward the outer spiral arm in the direction of Auriga and Perseus and Gemini. The winter Milky Way is real and observable on dark nights, but thinner and less spectacular than the summer view, because you're looking outward toward the galactic periphery rather than inward toward the dense core. For the southern hemisphere, this is reversed. Southern observers have the best view of the galactic center during the austral winter, May through August, when Sagittarius is high in the sky, and the Magellanic Clouds are visible year-round from southern latitudes, those two detached satellite galaxies that northern observers never see because they never rise above the northern horizon. The variation in the galaxy's visibility across the year is a consequence of Earth's orbital geometry, and it means that every clear night, in every season, some part of the Milky Way is accessible to anyone willing to get far enough from city lights to see it. There is no month where the galaxy is gone. There is no season where you can't find it. It just looks different depending on which part of the disk you're facing. The visibility also depends on where you are in your life, where you live, how old you are, how many dark nights you've had. A person born in a rural area 50 years ago may have seen the Milky Way every clear night of their childhood, have a bone-deep familiarity with its seasonal rotation, with the summer core and the winter disk, and the constant availability of it on a clear, cold January night. A person born in a major city in the last 30 years may have genuinely never seen it, may have no experiential reference point for what it looks like, may have to take it on faith that it exists. This is one of the quieter losses of the electric age, not catastrophic, not urgent, but real. An experience that was available to every human being for 100,000 years, free, requiring nothing but a clear night and open eyes, has been removed from the daily lives of more than half the world's population. The galaxy is still there. We've just made it harder to see. Supernovae have left scars on the Milky Way that we can still see today. Not the supernovae happening now, though new ones do occur in distant galaxies, often enough that amateur astronomers catch them regularly. The ones in our own galaxy are rarer, separated by decades or centuries, and the last one visible to the naked eye from Earth was SN 1987A, which exploded in the Large Magellanic Cloud, close enough to affect the entire astronomical community. But in the disk of the Milky Way, there are hundreds of supernova remnants, expanding shells of gas and dust, still glowing centuries and millennia after the explosion that created them. The Crab Nebula is the most famous, formed in the supernova of 1054, documented by Chinese astronomers who recorded the appearance of a new star in the sky, bright enough to be visible in daylight for 23 days, and visible to the naked eye at night for nearly 2 years. That explosion happened roughly 6,500 light-years away. The light arrived on July 4, 1054, by Western calendar reckoning. The Crab Nebula we see today is that same shell of gas, still expanding at 1,500 kilometers per second, about 30 light-years across now, still powered in part by the rapidly spinning neutron star at its center, which rotates 30 times per second and drives continuous energy into the nebula through its powerful magnetic field. The Vela supernova remnant, about 800 light-years away, is the product of an explosion about 11 to 12,000 years ago. Ancient enough to be enormous, about 100 light-years across, old enough to have cooled significantly. But the pulsar at its center, the Vela pulsar, still spins 11 times per second, and traces of the shock wave that swept through the interstellar medium when the explosion happened are still detectable. The Cassiopeia. A remnant is younger and more energetic. The explosion probably occurred around 1680, though the light was not widely documented at the time, possibly because dust along the line of sight dimmed it enough to be missed by the limited astronomical observation network of the 17th century. At radio wavelengths and X-ray wavelengths, it is one of the brightest objects in the sky, a violent, tumbling ball of superheated gas still in the early stages of expansion. These remnants mark the sites of individual stellar deaths. Each one is a memorial, a monument to a star that burned for millions of years, forged elements in its core, scattered them in a violent death, and left this glowing shell expanding through the interstellar medium as evidence that it was there. The Milky Way is full of these memorials. Most are too faint or too old or too distant to observe clearly. But they're there, the ghosts of stars, still glowing. The way the Milky Way is likely to be experienced by any hypothetical observer elsewhere in it, or in the universe, is worth thinking about. From inside the Andromeda Galaxy, the Milky Way appears as a small patch of light in the sky, similar in appearance to how Andromeda appears to us. A fuzzy smear, slightly elongated if you know what you're looking at, perhaps resolvable into individual stars near its edges with sufficiently powerful optics. The internal structure, the spiral arms, the bar, the Fermi bubbles, all invisible at that resolution. Just a glow. 2.5 million light-years of distance, compressing all that complexity into a point of pale light. From the vicinity of a distant galaxy cluster, the Milky Way would be invisible without a powerful telescope. One galaxy among hundreds in the local group, itself one group among thousands in the Virgo supercluster, itself one supercluster among hundreds in the observable universe. From outside the observable universe, if such a perspective were possible, the Milky Way would be entirely undetectable. Its light would not have had time to travel that far. It would be surrounded by a sphere of darkness, everything beyond the distance that light has been able to travel since the Big Bang, unreachable by any observation. We are embedded inside a bubble of visibility. Everything outside that bubble is causally disconnected from us. We cannot receive light from it. We cannot send light to it. It exists, presumably, but it is forever beyond any possible observation. Our observable universe, the sphere of space from which light has had time to reach us in 14 billion years, is not the whole universe. The whole universe is, as far as we know, vastly larger, possibly infinite. The Milky Way, in that context, is not a significant fraction of the universe. It is a tiny, temporary local structure in one small region of an effectively infinite expanse. And in that tiny temporary local structure, on a rock orbiting a mediocre star in a minor spiral arm, something developed awareness complex enough to work all of this out, to figure out that the visible universe contains at least 2 trillion galaxies, to determine that the universe is 14 billion years old, to photograph the event horizon of a black hole 26,000 light-years away, to detect gravitational waves from colliding black holes a billion light-years distant. In an infinite universe, we are a rounding error, a statistical ghost, so improbably small in scale that the word tiny does not begin to capture it. And yet here we are, asking the questions, getting some of the answers. Here is the thing that sits at the bottom of all of this, that all the facts and numbers and structures and timescales are circling around without quite landing on. The Milky Way does not need us. It was here for over 13 billion years before anything in it could look at it and recognize what it was. The spiral arms formed and wound through the disk. The bar assembled at the center. Generations of stars lived and died and enriched the interstellar medium. The central black hole grew. Satellite galaxies were consumed. All of this happened without any observer to register it. The Milky Way existed in total epistemic isolation, its structure evolving, its processes running, its history accumulating, with no mind to know any of it. That changed very recently. In the last 5 seconds of the galactic year, minds appeared in it that could recognize it, could measure it, could trace its history and predict its future. We are the Milky Way's most recent innovation, and from the galaxy's perspective, if galaxies had perspectives, the most unexpected one. Everything else the galaxy makes, stars, black holes, neutron stars, planetary systems, nebulae, even complex chemistry, all of it is a natural output of the physics of gas and gravity and nuclear reactions. But awareness, the capacity to look at the galaxy and ask what is it, and to begin to find out, that's something the physics of gas and gravity does not obviously predict or require. And yet the physics of gas and gravity produced it. Here, in this galaxy, on this planet, emerging from billions of years of stellar evolution and planetary geology and biological complexity. Something that can look up at the pale river of light and know, not just see, but know, that what it's looking at is 200 billion stars organized by gravity into a spiral structure 100,000 light-years across, with a 4 million solar mass black hole at the center and a dark matter halo extending 3 times farther than the visible disk, falling through space toward the center of the Laniakea supercluster at 600 kilometers per second. That knowledge is new. That knowledge is the most recent thing the galaxy has made. And it is extraordinarily strange that the galaxy can now, through the medium of the minds it produced, know itself. The ancient question, who are you? Where are you? What is this? Has been with consciousness since consciousness began. The Milky Way has taken 13 billion years to produce something that can start to answer those questions about the Milky Way itself. That is either the most remarkable coincidence in the history of matter or the most expected development possible in a universe that is what this universe is. We don't know which. Both feel true from different angles. The Milky Way is approximately where it was when you started reading this. The spiral arms are in the same positions relative to the galactic center because nothing moves on human timescales at galactic scales. The S-stars are tracing their orbits at the same speeds. The molecular clouds are collapsing at the same glacial pace. The supernova remnants are expanding at the same velocities. But something has changed, not in the galaxy. In you, if these things have done their work. The pale arc of light across the night sky is not the same if you know what it is. The faint smear that your ancestors saw every night, that they named rivers and trees and roads and fishes, is the edge-on view of a structure so large that 1 billion years of highway driving wouldn't cross it. It is hundreds of billions of nuclear furnaces, each one more massive than 1 million Earths. It is the remnants of ancient stellar collisions strung out in streams through the halo. It is a 4 million solar mass black hole photographed by linking telescopes across the entire planet. It is dark matter in quantities 5 times what the eye can see. It is the cosmic address of every human being who has ever lived or ever will. And it is, on a quiet, dark night, visible to the naked eye, a pale river, a milky circle, soft and diffuse and ancient, arching from one horizon to the other. Go find it. You live inside it.